Okay, so in here we'll try and discuss how to manipulate the different chemical equilibrium constants. Okay, so there are basically 3 different ways in which can do it. This is really simple. It must be a recapitulation for most of you guys. So we'll just do it quickly. So the first one is, so if you have any reaction, we'll just try and deal with this with examples, which makes it easier. Say you have a reaction which is something like this. So if we want to write the K equilibrium, which I call K1 of this reaction, this becomes over the reactants. Yeah, so the law of mass action. Simple. Now, if we just reverse the reaction, now we are trying to find out, so what is the relationship between the K of that reverse reaction and the K of this reaction? So let's write down the reverse reaction. So the K of the reverse, let's assume that is K2. So we find out that the K of the reverse reaction is something like this. Now this is just K1 inverse, isn't it? So what is the relationship between the K1 and what is the relationship between the K equilibriums of 2 reactions which are just reversed? It is just the inverse of each other. So if you know the equilibrium constant, which should be a number for any reaction, and someone is asking you to find out the K equilibrium of the reverse reaction, what you do is just do a mathematical inverse of this, right? So just divide it by 1 and that's the answer. You don't have to do the experiments once again. This is really simple. So chemistry becomes mathematical, it becomes easier, okay? So the second is, if you have any reaction or something like A plus B is giving you C, and let's assume the K is K3 in this case, which is C over A and B. If this is known and you just multiply the whole equation by a stoichiometric coefficient, and then someone is asking you, okay, like when you multiply this with the stoichiometric coefficient, what is the reaction constant, what is the equilibrium constant for that reaction? So let's assume this is K4. So this becomes C over N, and this N can be anything. This can be a fraction, okay? So I'm not taking special cases for fractions, and because it's the same thing, whether it's a fraction or not. So this becomes C A B over N. This is basically KH3 to the power N. Okay. What this means is that if you just multiply an equation with a stoichiometric coefficient, and if you want to find out the equilibrium constant of the new equation, all you have to do is raise that to the power of N. Okay, it's very simple. The third one is the most interesting one, because this will combine 2 equations. Okay. Now let's assume you have a reaction. Let's see simple cases. So in here, let's assume K5 is C over A and B. Okay, let's take another reaction in which you have P plus Q gives R, and the K6 is simply R over P times Q. Now, if you add these reactions, right, if you add these, you get a new reaction in which you have A plus B plus P plus Q gives you C plus R. Okay, and then now let's assume that the K equilibrium of this reaction was K7, which was C times R over A times B times P times Q. Now, you can say that this is just the product of these two, right? So if you just see it here, you can see C over A by B is basically K5, and R over P and Q is basically K6. Okay? So if you just add these reactions, when you add reactions, you just have to multiply the two equilibrium constants, and that will be your result. The same goes for mathematical subtraction. Like if you just subtract it, you just have to divide it, right? So you can play with this with all these three together, and with these three rules, you can convert any reactions. You can manipulate any chemical equations mathematically. So this becomes easier when you don't have to do an experiment again. You can just use the K equilibrium that you got for one reaction, one equation, and you can mathematically manipulate it. Okay.